right, so we've looked at momentum and the change of momentum, also called an impulse. And now we're going to look at something called the conservation of momentum in one dimension. Actually, it works in all dimensions, or in two dimensions as well, but we're going to focus on one dimension here. And the law of conservation of momentum is that if the net external force acting on an object or system of object is zero, then the total momentum of the system remains zero. So all that is saying, it's a fancy word of saying if there's no outside influences, the momentum that you had before, so rho, is equal to the momentum that you had after. And to know that, we have a little mark there. So we have momentum before and we're going to talk about collisions. Momentum before equals momentum after, as long as there's no outside force coming in. So in a closed system. Oops. There we go. Now this could also look, because we're going to deal with a lot of subscripts and different variables, you could also have something like this where your rho initial is equal to your initial or final momentum. It's another way you could do the notation. There are several different notations for it. Now, like I said, we're going to deal with collisions. And so, for instance, consider a head-on collision between two objects. You have first object here with mass 1 and a velocity 1 hitting a second object which has mass 2 and velocity 2. Now afterwards, they're going to have a different velocity, although the masses are definitely going to be the same. But overall, even though the velocities change and the masses don't, the momentum will stay the same. Now again, this is the up above. Those formulas there are the representation, but the more specific formulas that we're going to use is that if you're looking for your momentum before, well, you have m1 times, what do they call it here? VI, initial velocity of object 1, all right, plus you have m2, and then you have the initial velocity of object 2. And that would be the total momentum before. And looking at the momentum after, so this would be, the initial momentum, put an I there, final momentum, again you see all the little subscripts. Well, the momentum of the first object after the collision would be m1 vf1 plus the momentum of the second object afterwards, which would be m2, then times its final velocity of object 2. And there we go. Now, again, there's different ways to do notation. Or, how I look at it is, this makes a little more sense for me just because it's easier with the notation, is that your momentum before, I just have nothing there. We have an m1, so that's not going to change. But we have a v1 plus m2 times v2. And so that doesn't really change much, but my final momentum total, I put a little symbol there, prime, for those of you who are in calculus. That's your prime symbol. All right, so then we have m1, still v1, but prime. And that prime is indicating that's after the collision, plus m2 v2 prime. Now I like this notation better, but again, there's other ways to notate because you got multiple velocities here. Essentially, you've got 4 different velocities. V1 before, V1 after, V2, and then V2 after. So again, it's hard to, with all the different notation going on there. All right, so using the conservation momentum, 1,400 kilogram cannon, which includes the 50 kilogram ball, is on wheels. The cannon fires the cannonball, giving it a velocity of 50 meters per second north. What is the initial velocity of the cannon the instant after it fires the cannonball. All right, now, initially here, our cannonball and cannon are not moving. So regardless of what their mass is, the initial momentum is 0. All right, now what we're going to find out is our final momentum, which is also going to be 0, but we're going to find that final velocity of the cannon, not the cannonball, but the cannon. All right, so we have information, our M1. I guess the cannon will be our first object. It's 1,400 kilograms. M2. Whoops, M2. We have the cannonball, which is 50 kilograms. Oh. Let's see here. Yeah, 50 kilograms. All right, now, the final velocity. So our V, how am I going to write this? V1 prime. Yeah, that's how it works. That is the cannon. We don't know its velocity. Now, V2 prime. The cannonball. Get mixed up here. Let's see here. We have 50 meters per second north. All right, so I'm going to say 50 meters per second, and that's going to mean north. All right. So now I know that this final momentum is equal to 0. All right, so that means that our V1, because again, our velocities when they're in the opposite direction are going to be negative. All right, so our final velocity, which I'm going to have to use a pen here to write down. So we have rho prime is equal to 0. But again, it's equal to M1 times V1 prime plus M2 V2 prime. All right, so 0 equals. All right, so I'm plugging in. M1 is this 14 kilogram cannon. We don't know V1 prime. Oops, prime. Plus, we have the 50 kilogram cannonball. And the V2 is 50. Now, I'm going to go with positive 50 because I'm going to say that north is positive, which again means south is negative. All right, so now do a little bit of math here. I got 0 is equal to 1,400 V1 prime. And then I got 50 times 50, which I believe is 2,500. All right, so now I'm going to move that negative 2,500. All right, to the other side, so it becomes negative, and then I have 1,400 V1 prime. All right, now my last step here is that I'm going to divide both sides by 1,400. And what I get on one side, I do to the other here, and it looks like my V1 prime, the velocity of object 1 after the collision, is negative, whoops, got a calculator here. I take negative 2,500 and I divide it by 1,400 and I get negative 1.79, which is another way of saying that the cannon is going to kick back at 1.79 meters per second, but in the opposite direction, which of course is south. And there we go. All right, let's try one more of those. A little bit different situation. A railway car of mass 5,000 kilograms is moving left at 2 meters per second. It collides and combines with a freight car of mass 2,000 kilograms rolling to the right at 3 meters per second. What is the speed and direction of the pair after the collision? All right, so they hit each other. One's moving left, one's moving right. Whoops, I guess this way. So they hit each other. All right, and then they combine. But again, momentum before, is equal to your momentum afterwards. Now, getting some of our values down here. Our first mass, I'm going to say, is that 5,000 kilogram car. And it is V1 is moving 2 meters per second left, which I'm going to make negative this time out when we get there. Now the second object is the freight car, so that's going to be M2, which is rolling in at 2,000 kilograms. And it is moving, so it's going to be our V2 here, at 3 meters per second right. Okay, now what we want to know is a couple of things, or a couple of things we do know, is that they collide. And so we're going to have a mass, total mass, because they become one object. And when they collide together, they become 7,000 kilograms. And what we want to know is the speed and the direction of the pair afterwards. So I'm just going to call it V prime. It's V1 and 2 together. And after the collision, that's why we have that prime there. All right. So now, just to kind of look at our formula here, see if I can fit it in all in big letters, is that our initial momentum is M1 times V1 plus M2 times V2, and then it's equal to, well, the total momentum when we only have two objects, or sorry, one object. So we have our total mass times our final velocity. Hopefully that makes sense. This MT there is one value, the mass total. Maybe I should do a big M and a little t. I don't know. There we go. All right, so now I'm going to sub my values. But again, as I mentioned, I'm going to make right here, let's go with positive, and left negative, because that's normally what I do. All right, so subbing in values. M1 there is 5,000 kilograms. Our V1 is 2, but it's left, so I'm going to go with negative 2 on that one. All right, plus M2, which is our 2,000 kilograms, and it is going 3 to the right. And our total mass was 7,000 kilograms, and we want the final velocity of those two together. All right, next up, a little simplifying and rearranging. Well, 5,000 times negative 2 is negative 10,000. And then 2,000 plus times 3 is 6,000. And again, that's equal to 7,000 times V. All right, lose 10,000, get 6,000 back. You're still down 4,000. All right, and then my final step here, so I get both the magnitude and direction of this velocity. So I'm going to divide here by both sides by 7,000. And there we go. And so our V prime, our final velocity of both those objects, I take negative 4,000 and I divide it by 7,000. I get negative 0. Again, going to two decimal places, 57, which really means the final velocity of these two is 0.57 meters per second, but that negative sign means we are headed, it's going left. So that means the object that was going left had more momentum to overcome the object that is going to the right. Now if I look, the object that was going right was faster at 3 meters per second, but it definitely wasn't as heavy. It was actually 2.5 times lighter. And so it had much less momentum, and that's why the railway car with the much larger mass, it ended up going in its direction. But again, the total momentum that you had before is equal to the total momentum you had afterwards.